So, very welcome back to my machine learning experience where I am trying to implement a convolution with padding and strides and also doing the backpropagation for that. So I will today describe you my implementation of the backpropagation. You can see that the code itself for the backprop is not too long, but I have to explain what is going on here actually. So first of all, let's do some mental refreshments on backpropagation through the convolution layer. So as I talked about it in my last video, and probably you already knew it, if you are in here for this, then you know how it works. So usually in a neural network, an artificial neural network or deep neural network, whatever you want to call it, you have all these linear combination steps like the fully connected layer or like the convolutional layer, and then you will probably have some nonlinearities introduced in some way or another. But this time we are only focusing on the convolution part of this equation, and convolution is, as I already told you, just a very fancy kind of linear combination of weights and the input. So let's consider this very simple and primitive examples where, let's say, we have y1 and y2 as our outputs of our system, and this output comes from a bias that, and then a weight 1 is multiplied by x1, and then we add weight 1 2 multiplied by x2, and the y2 it has the same b bias. So this is called bias because it doesn't depend on the input. So it's bias plus this weight 2 1 and weight 2 2. It's linear combinations of x1, x2 with these different weights. So in some cases, if you took the Coursera course for machine learning, this basic machine learning, you can like implement this in a full vector multiplication, and you just say that b is always multiplied by 1, and so you make like a quasi vector from this x1 x2, which will include 1 x1 x2, and multiply that with a vector of b w11 w12. But in some other books, if you read, they will just separate this bias out. And usually when it comes to convolution, it seems to me that the bias is just like described like I wrote here, just like this. So that's why I think, and yeah, because yeah, in this convolution case, I think this is the most straightforward way to look at it, because how these weights are interacting with the different x's is very different with how the bias comes into play. So, and then we have the cost function. I already wrote these equations learning from the last video, so I just put them way down there so I can delete the enters and it can come up to you. So it's 2019. This is how we do presentations on the internet. So then we have the cost function, which it is just a simple sum of squares kind of cost function. You can use different cost functions for different purposes. It doesn't really matter in the grand scheme of things. Here we just use this cost function because it's very simple to find the derivative. So what we are doing is, so this is the y1 we got from this equation, this y2 is the y2 we got from this equation, and then we have some measured y1 and y2 values. So this y1 prime and y2 prime, you have to consider that like the target of the value, like you are making a prediction, and the prediction you make is the y1 and y2, and the value that you should be getting, so the real value will be this y prime and this y2 prime, y1 prime, y2 prime. And this is called the cost function because I guess if your predictions are very different than what happens in reality, this number will be very big, and that will cost you a lot of money if you screw up your predictions. I don't know what. I just came up with this explanation, so don't take my word on it. So we have this magical 1/2 here for the cost function. We want to minimize the cost function. So we want this cost function to be as low as possible. So we want y1 to be close to y1 prime and y2 to be close to y2 prime at the same time. So we have this kind of assumption that both of these prediction values worth the same in this case, because both of them should be as close as possible. But like if this is more important to be closer, then this should have a bigger impact on the cost function. But whatever, we don't really do that. I don't think we do that. You can do that, but I don't think people do that. But I might be wrong about that. Anyways, you have the cost function. You want to make this cost function minimal. You can make up any cost function. But I'm talking too much about this cost function. So you want to make the cost function as low as possible. And as I told you last time, and as you might know, to have a low cost function, you must have you must find the derivative of the cost function, because that way, so you want to modify like the base, or you want to modify the weights. So the x's are the values that you cannot modify usually, because this is what the data you want to get your predictions on. But anyways, so you want this cost function to be low by changing the b and the w values, and this is, for example, the derivative of the cost function differentiating with respect to w11, and we use, so if this differentiates, so the derivative of cost function with respect to this w11 is positive. That means that if we change this w in the positive direction, so it goes up, then cost function also goes up. This is not what we like, so then we will, of course, consider that. If this is a negative number, then it means that if we increase the w, the cost function will go down. If it's 0, then it means that we are in a place where the movement in neither direction should change the cost function. In reality, that doesn't mean that, because this only applies to an infinitesimally small number. So in reality, when your cost function is, or the derivative is 0, that usually means you are either in a maximum or a minimum place, or in what is it called when, I don't know. I don't remember my math. Anyways, but so you want to get to this, because they will tell you which direction should you change this weight to change the cost function in the desired direction. In this case, to change the cost function to be lower. So we apply the chain rule, because here you can see this equation. There is no w1 in here, but it's implicit because it's part of the y1 and not part of y2, but it could be. So this cost function is basically, we apply the chain rule, so we have the y1 and the y2s. So y1 depends on this, and y2 could depend on that, or maybe it doesn't. We don't know, maybe at first look. So we just say the cost function derivative by with respect to y1 times the derivative of y1 with respect to this weight. And of course, same comes for y2. So let's see, what else can we say if we have this cost function. Okay, let me scroll a little. So we derive the cost function. We differentiate with respect to y1, so the derivative will be this function by this. And of course, this will mean, so you can figure out the derivative of this is going to be 2 times y1. This is going to be just 2 times y1 prime, and the derivative of this with respect to y1 is 0. So I did not write it out because it's very simple. So because it's just there is a multiplication by a constant, so you can get the multiplication of the constant out here to the front, and then when you can use all this. You can take where are my brackets? Okay, so you can just go one by one every part of this additions and the what is this called? So the minus and the plus. You can just take it apart, and the derivative of y1 squared is not else but 2 times y1, and the derivative of 2 times y1 prime y1 derivative is 2 times I can y1 prime, which is going to be this. So we'll get the derivative. This is the cost function derived by y1. So we'll have this part here will be multiplied by the y1 differentiated with respect to w11. Yeah, and this is maybe I should write that. I didn't write that down because it seemed like, kind of trivial what's going on there, but let's just spend some time on that. So if we want to calculate this part, so cost function, that's gonna be the derivative of this by this, and we know that's simply going to be x1. So if you go back here, let's go back here and let's see. So this is going to be y1 minus y1 prime. I should put the not here inside the bracket, and will be multiplied by x1, of course. And we did not do the other half, but we know that that's going to be the very same thing as here. So cost function the differentiated with respect to y2 is going to be almost the same, but it's going to be y2 and y2 prime, because it looks same to me, at least. And what is going to be multiplied by is the y2 derived with respect to, so differentiated with respect to w11. But w11 does not appear here, so it's going to be 0. So when we multiply something by 0, we know what's the fate of that. Shit! This is the fate of that. Okay, so it goes out of the window. And we can usually just say that, this is, what is this? We can just have a shorthand for this, call it like dy1, or if we have a nice Greek letter delta there, it's not the Greek letter delta, I think, but anyways, it looks similar to Greek letter there, the Greek letter delta enough to me. Okay, so this is what happens. So you will have this delta y's and will be multiplied by this x1 here. So basically, conclusion here is that y1 was influenced by w1 like this. So the derivative of the cost function with respect to the w11 will be x1 times this delta y1, where delta y1 is this expression here. It's gonna be, of course, different if you have a different cost function. But in any case, you can get you define this delta y1 in any way, and you can use that in you just calculate it for every every output you calculate that delta, and you just use that. So this will, of course, if you do the derivation with respect to W12, so you differentiate with respect to W12, then it's gonna be delta y1 times x2. If you do differentiation with respect to W21, that's gonna be delta y2 times x1, and if you do it by the bias, then we already know it's going to be this is going to be the delta y1, and what is the delta y1 differentiated with respect to the bias is 1, and what is y2 differentiated by the bias is going to be also 1. So the bias, the cost function by change of the cost function by the bias is going to be just delta y1 plus delta y2, which is, if you think about it, so if you change the base, or I'm saying base, if you change the bias a little, move up, that will change both y1 and both y2 to increase the same amount. So it's going to be like the 2 times of that increase, and that will change this some way, and this change it some other way. It's gonna, it's not. Anyways, you get what I'm saying. So it's gonna change in both of this and both this. And how will it affect this? So it changes y1 and y2 in the same amount. So the only thing what it will depend on how it changes is that already how this relationship works out. So this is how you should think about it. It's kind of very intuitive, not going into more mathematical details. But anyways, so this was the intuitive picture. So in case of the convolution, of course, we have this much more complicated thing. When, like, let's just click on this. So like this y value will be influenced by all these and all these things. So these are the x's, these are the weights, this is the bias. And of course, what I did not say here is that even though I just said in the beginning that we don't change the x values because that's the measurement points, that's the data we base our predictions on, so you do not change the x, but sometimes, and not just sometimes, if you have a deep neural network, so when you have more and more layers, then you will have another layer. So this x1 may be coming with another, so it's maybe, x. Let's just go back one line here, and if I just say maybe this x1 is coming with, like, let's just say v11, and let's just make up some random letters here. These are totally random letters, don't take this too seriously. Anyway, so this xy maybe has some other, maybe it's not the data we got. Maybe it's derived from our real data. Maybe the real data is R1, and we got this from another, thing, another layer. So we have to go back one step more. So if you want the find out the you want to differentiate the cost function by this one, then you have to figure out how it works by what's the cost function by y, what's the derivative of y1 by x1, because that's what, and then what's the derivative of x1 with respect to this v. So that's why you will have to calculate the derivative of cost function by x in every multi-layered case, and you will, if you want to do deep learning, then that's how you go deep. You have more layers. So we have to figure out here And this is what I want. This is going to be the bottom part. Will be some parts of the calculation. I did not calculate everything, every derivative here, because it's kind of complicated to do it by hand. But I prepared, so I'm not going to do the clicking and missing and clicking and missing this time. So let's go through this backpropagation algorithm here that I have in my nicely named convolve.py. And so what does it do? Calculates the derivative of the cost function by the kernel and the input elements based on the derivative received as dy. So dy is going to be everything that comes after this. So if it's more layers, then it's going to be the derivative. It's derivative of the cost function by the output of this layer, which can be like the final layer, which can be another deeper layer. So that's what is going on. So we get dy, we have this very short set dy algorithm here. It only checks, so dy should have the right size. Then this instance of this object will store this dy value, so that's it's only get the regularization parameter, because sometimes you want to regularize your things. I'm not going to talk about regularization now. Maybe next time, maybe some other time. So it will return the derivative of the cost function by the elements in the kernel. So the kernel is the weights. Basically, the bias is the derivative of the cost function by bias element, and dx is the derivative of cost function by the input elements. So these are things I was rambling on and on about. So of course, if the sizes are 0, so then it's just false, false, false. It's just kind of checking if you already have the things you need. Okay, so dx, dk, so it should have like the same shape as the x. It should have the same shape of the k, so the kernel, and it should have the same size as the bias vector. So which is f, which is how many. What is the f? What's f? So f is the what? Anyways, it should be how many layers, how many output layers we have, which should be it's not the depth of the convolution, it's the it just doesn't come to my mind. So where do I define these names for myself? What? Filter number! Oh my god, sorry. My brain totally froze on that one. Okay, so filter number. Anyways, the number of output layers is the filter number. Okay. So what's the d bias? So this is going to be derivative of the cost function by the bias. So with respect, it should be with respect to. Yeah, this is how you know that I never learned algebra and analysis in English. So it's with respect to. Anyways, so the bias is very easy. You just sum up. So dy is going to be, it's a 4-dimensional tensor. And so basically we have here, you see like the bias, so it's every cell in this matrix is influenced by this bias. Every cell in this matrix is influenced by that bias. So these are 3 different inputs. So these are 3 3 samples. All 3 samples has 2 layers, and all 3 sample has 3 layers in the output. So each bias contributes to each and every cell in this layer. It contributes to all the samples, it contributes to all lines, and it contributes to all columns. That's what happens here, is that we sum up. So the 0th axis is the sample number, the first axis is the layer number, and the second and third axes are for the x and the y, so rows and columns. So you can see that we sum up all by these axes except for that, and this is going to be my sample for the dy's. So I just put a random, like ones in random places. Every other place should be considered as 0, and this is how this application works. So when I go here, it's just I sum up all these numbers. So everything here is summed up. So all the dy's of these are summed up in the derivative of cost function by the bias. Derivative of cost function with respect to the bias. So this is kind of easy, because bias is not influenced by the actual input values. So bias was very easy. What happens with the x is, it's gonna be, so first we do derivative of x, and what we're gonna do is get a reshape of the x matrix. So this reshaping, this is the same as I talked about in the convolution part. So this I don't have that prepared. But basically reshaped x is making these 4-dimensional tensors into just 2-dimensional matrices, and it flattens out the kernels too, and basically transforms this convolution operation into a simple matrix multiplication. And here, what I'm going to do is I get this x and reshape it, and then I will flatten these the dy, so the derivative of the cost function by the output elements. And then how do I do that? I just transpose the dy, so I mix up the first 2 axes. So if you remember how we did the convolution, in the end we had to change the axes. Maybe I should have brought up my other file there. Anyways, so what is so just to remind you how it worked. Yeah, I should do that, but I don't know how can I. Yeah, this is going to be here somewhere, this one. And don't use my file structure against me. So let me bring this into view. So this is how it worked. So basically, well, it's not as well self-explanatory I was thinking. Anyways, so we make this. This is the kernel flattened out here, I guess, and this is, or is it? Yeah, this must be the kernel because it's 2, 1, 0, -1. So it's basically like going backwards in this part, so backwards for the x and the y values, because we flip the kernel when we do the convolution, if you remember, and like this part of the image is flattened out like this. And this is like we take the kernel and then by the and this is gonna be 2 layers, and then this is gonna be the, oh yeah, it's not it's not as well describing this as I remember. I probably have talked a lot and have shown not much. But anyway, so how it comes to life is that the kernel is here, and the kernel has 2 output layers. So it has like the 2 rows, and that's how the flattened y values also have 2 rows, while the x is flattened like this, so all the parts are flattened. So when we're trying to reshape it into like a regular image, we have to so reshape it, and we have to kind of, you know, like how is it stored in the memory is like we go through the first line and the second line. And the first line will have all the rows, and then all the columns, and then the samples, and then the layers. So when we reshape it first, we reshape it in a shape of layer first, then the sample number, then row, and then column. And then we have to change the first 2, flip the first 2. Yeah. Sample, yeah, this is written here. Yeah, exactly like this. And that's what we do. So we reshape. This is basically very easy because this part with the y values is just flattened out like lines and rows and columns, like I mean columns and rows. So each line is here, first line, second line, third line, and then next sample, first line, etc., etc. So very easy. We change, so we transpose this tensor the way we need to, and then reshape it so it has, for the x coordinates, so for the number of the rows will be the number of the layers, the filter number, the layers in the output as it was in this. So this is, you know, the first, it's going to be like the 0th, it's exchanged there, and then all the -1 tells NumPy that just, you know, divide the number of cells in that, and that's gonna be with this number, and the remainder like just flatten in that many rows and find out how many columns there will be by yourself. And then what we do, lo and behold, we do a matrix multiplication here, which is not this, but this one. So instead of this matrix multiplication, so remember what we have is the dy's and the x's, and we want to figure out how to calculate the dk, so which is the weights, so which is the derivative by the weights. And what we learned from here is that we have to multiply the deltas or the d's. Yeah, you cannot use the delta symbol and a variable name to the best of my knowledge in Python, so that's why it's just dy. So multiply that, the output that it affected, by the input that this output value came from somehow. So here it's very straightforward. So this value is coming from these x's and these kernel numbers, and this pairs up with this pairs up with that. So you can see like each goes and pairs up with that. So how can we basically do that? We multiply this delta y value with this to get that, and multiply this delta y value with that to get that. multiply this with that to get that. It's going to be the reverse matrix operation. So we can do the matrix operation because you have like, there is one matching dimension here. So let me go back to the code. So we transpose the X matrix, which means this flattened X, it's instead of being like this, let me just, I was not planning to do this, but I'm going to do this. How can I come? I wanna, yeah, let's put it after this. I mean after, so here I want, how could I do this easily? Yeah, maybe I should not have copied it, I just shouldn't. Yeah, just delete everything. Like at least delete, oh my. No, that's too harsh. Anyways, let's copy this and by numbers and by format, and then I just copy this format here and just delete everything here. So we have the x's flattened and the flattened version of the dy's. Let's just give it like, let's make it -1. And then when I transpose this, what happens if I transpose this? Let's see. So transpose, and then I can just get rid of this. So I transposed it. Now you can see that the dimensions are matching up for a matrix multiplication. And what you're gonna get here is exactly how many layers does your kernel have, and what will be this dimension. It was how many elements were in the kernel. Oh, this formatting was screwed up a little. So this is like the kernel went like, 1, 2, 3, 4, 1, 2, 3, 4 for the second layer, etc. So now by doing this matrix multiplication here, you will get the matrix, which is exactly the dimension of the flattened kernel. And it also has this strange beauty that all these numbers here, that y numbers, so these coming from these, were influenced by this kernel, and now this derivative by the kernel, derivative with respect to the kernel, is also coming from these y values, so that's fine and dandy. But then also, if this one, so I want this one was influenced by this x value and this y value and this x value and this y value and this x value and this y value and this x value and this y value, and now we have all of them prettily beautifully paired up and multiplied by each other. Oh my. So this is how you get the derivative with respect to the kernel. It's quite straightforward. And then what's gonna happen with the dk is very easy. We have to reshape it back to its original form, so filter number, depth of the input, and the kernel size. We are working with squares here, and then we have to flip, so the ordering should be, it's a colon, colon, -1, colon, colon, -1. It basically reverses the order of the elements there. So this is how we get the decay. And of course, if we have the L2 regularization, then it means that the higher the kernel is. So anyway, don't worry about this part because this is regularization. I'm not talking about regularization now. So we do not regularize the bias, so that's why there is no regularization there. And how do we get dx? Very easy, just run this function. Yeah, what is this function? So this function is this. It's more intricate. This is the most intricate part, and now we are already at 40 minutes. So now brace in, because now it's gonna be hard and brutal. So how much padding do you need for this? So you need to pad your dy matrix. Why do you need to pad it? And so let's take a look here. Why do you need to pad it? Is because, so if you want to figure out what was influenced by this cell, we can do that here. Very easy. Oh my, a lot of things, but don't care about this one because this is going to be for the backpropagation. So this one influenced these outputs. So if we go, let me delete this. So these three, it was these three. So this one, this was influenced by this multiplied by this value, and here it was multiplied, I guess, by this value, and here it was multiplied by this value. So it has quite, like these three dy's have worked with these three w or k values of kernel. We're going with the k because it's kernel. Okay, that's fine and dandy, but let's go in the middle of this and let's show. Oh, but this was influenced by 4 of these elements in each of this. So what it means is that when you're trying to go backwards, some of these will fall to the sides. So like this on the side, you will have to treat like this when you calculate this delta x, so the derivative of the cost function with respect to this x value, then you will have to consider that this is only influenced by this, I'm sorry, this with this and this and this one. So all these other parts were influenced by nothing. So there's like this 0. We can like pretend like there are zeros around here. But when you move more inside here, in the inside of these parts, then you will see that like this was influenced by, now I'm not quite sure which. So this was influenced by these 4, and this was all probably, coming together with these kernel elements, and here it was coming together with all these 4 kernel elements. And if you go to like this side element, it's kind of obvious if you look at this that when you are going backwards, you do have to pad these, because the thing is, when you go backwards, it's going to be a convolution. It's going to be a convolution backwards because it's going to be, this element will be influenced by all these 4 elements that it influenced, and it will be influenced by the kernels the same way as it influenced them by the kernels. So you cannot really, there are a lot of good graphics on the internet that will do it for you. And the padding, very easy, will be the kernel size minus the padding you used for the x, for the convolution operation, the forward propagation, minus 1. Because if you used convolution, so if you use padding in a convolution, so you padded this with zeros all around, then you would get more elements at the sides that were only influenced by this multiplied by this part, because these three parts will be multiplied by the zeros, so they fall out. So this multiplied by this part would be on the side. So then we would have all the four elements here around influenced by this x value with these elements in the kernel. So it's kind of, the more you pad for the x part, the less padding you will need here, because instead of the padding you will have real values already at your disposal in the y matrix. I hope that's kind of clear enough. And then comes the other part, which is very hard to find any good source for on the internet, and this is how you deal with the striding. Because if you stride during the convolution, that will mean that you will basically leave out parts. So if I did striding here, I would miss these elements. So these numbers wouldn't be here. If I did like a stride of 2, there would be just this with this, and then this with this, and no this with this. Okay, I was using, hope you were watching and not just listening. And then, of course, everything would look very different, but when you're going backwards, you will still need these numbers if you want to just do a regular, like you don't want to complicate it, you want to do a convolution backwards. So you would need these parts here. So what's going to happen? So you need to multiply something with this, and these are zeros because they are not here anymore. So what you do is dilute. And so we make a dilute. This is going to be a matrix of zeros. And then it's a very kind of a smart way to, I'm saying smart because I did this, but it's a way to, so we start from 0 and we go to the y, size of the y matrix times stride minus stride plus 1. So it's not like, it's kind of convoluted how it comes together, but the matrix for diluting the dy has a 1 in every column that are spaced out by stride minus 1, zeros between them. So the matrix height is this. So take a moment to read it. And then let's try this. How will the dilution matrix look like? So let me just make a very simple demonstration what really happens here. So I'm going to make an A matrix, which is in NumPy, and this should be NumPy. No, it's just an array. Let's just make an array. Let me make an array here of just a few numbers. So now, oh come on, yeah, I need to close this bracket. Okay, so now I have an A matrix here. Let's say I wanna dilute it with 1, so we had the stride was 2, so we dilute it by stride minus 1, zeros. There's gonna be 1 zeros, we wanna dilute it. So let's make the dilution matrix is going to be a NumPy array. Let's just make it NumPy zeros for the time being. And the shape will be, so it will be 5 by 3, because so it's the y size, That's good. It's 3, and this self, so self dot y size is y size times the stride minus stride plus 1. So this is the other expression here is y size plus y size minus 1 times stride minus 1. So what it comes to is basically, so stride is 2, stride minus 1 is 1, so I need to dilute with 1 zeros over, and I'm not, this is, the size will be, so because I don't want to put zeros on the sides, I want to put the zeros only between the elements. So if you think here, like if I had, instead of this, my output would be just, 3, 3, 3, 3, like that, and I want to put zeros between here and between this, but I don't want to put zeros on the sides, I don't want to put zeros on these sides, just in the middle. So that's how you should be thinking about this. So I make this dilution matrix, and well, I have to figure out what parts I make 1, and those will be the, let's go with the numpy's arrange function. So it's gonna be the 0 of, and then it's gonna be the stride is going to be 2, so it's gonna be 2 here, and then it's going to be the y size in this case is 3, and the self stride, so the stride is 2, so it's gonna be 3 by 2, so that's gonna be 6, and minus stride, that's 4, plus 1, that's 5. Yeah, so this is basically same as this 5 here. Yeah, this should be the same, probably. Why do I have this brackets here? This brackets makes no sense. Anyways. Okay, let's do this. Whoops, what did I do wrong? Yeah, of course it has to, and this is not a function. It's yeah, I'm coming from a quick basic background. It was 20 years ago I learned quick basic, so now I can blame all my bad syntax on that. No, actually, I also programmed a lot in Visual Basic Script in Excel, if I can tell you that, if it's not too much a shame to do that, but anyways. Yeah, and then it's just, the other side is just every, it's gonna be every part, so it's y size of 3. Okay, so now we got the diluted, this is gonna be the dilution matrix, and you can see that we have a 1 in every column, but we don't have a 1 in every row. And then we have the A matrix, so we want to multiply diluted multiplied by A multiplied by, and let's watch the magic, diluted transpose. Ta-da! So what happened here is we multiplied this A matrix on both sides with the dilution matrix, and we got all these nice zeros in there. Let's just make the B matrix, and you can see it's better. So we got all the original values diluted, and now that's good. So this is what happens here. Exactly, we dilute this y after padding, and then after that we do some reshaping. Then we do some transposing and reshaping of the k. So here basically we use this image to column, is flattening diluted. So we got the diluted Y matrix, and after we diluted it, we flatten it with this image to column, and then we do this K flat is going to be coming from this transposing and reshaping. So which is basically doing a convolution. So we flatten, and do the matrix operation, then reshape them back to its original shape. So that's how we get the flat dx. This is basically the same, almost the same, what we do with the convolution. So what's different here is that we are not changing, so we are not reversing the direction of the kernel. And why? Because if you really think about it, so this element, so this one comes from here. So it's kind of hard to see, but this one is from when it comes to this and this. So this one is multiplied by, this one multiplied by this. So this one multiplied by this results in this one here. And this one multiplied by this results in this one here. And this one multiplied by this will result in this. And this one multiplied by this will result in this one. Well, it's not, because I'm using the wrong matrix. It should be here. Oh my. Anyways, or this should be this. But what happens here actually is that when you go backwards, let's just think about it. So let's just think about this one. So when I want to go back here, like go to this part, what influence did I have? Then what you will see is that this one was influenced by this multiplied by this. Because when we are calculating this, then we are using this part, this with, come on, this with this with this one with this one, this one with this one, and this one with this element to get to there. So this is multiplied by this one to get this, and this is multiplied by this one to get that. So basically, when you are going the backwards process, you are not doing a convolution, actually, you are doing a correlation operation. So backpropagation for convolution is going to be correlation. So that's why you don't flip the kernel before or during flattening. And then you basically do the same thing as we did when we were doing the forward propagation convolution. So let's just do this testing here. So I already imported this W by S, X, and dy. And what I want to do is let's just make this convolution layer here. We got the Y, and then just set the dy and go back to the dw and the d by s and the dx, and we got all these things. And it's gonna be neat. So here I did this to kind of calculate some things. So here, because it's all these three elements from this will have influenced this matrix. So I just got like all the elements that were coming from here are multiplied by the corresponding parts from the x they were multiplied by, and this one goes for the second. So this one is going to be coming for this element in the kernel. So used all these parts and these parts mixed. This one uses all these parts and all this. And if I did the same for all the three elements. So we can just look at this one, for example. So here we are multiplying all these elements. So it's like, let's go AQ17 is this element multiplied by M2. So this is M2. And then you go AR17, which is this element multiplied by N2. So it's also very similar to the convolution. It's also correlation operation actually between these two elements, but I did not implement them this way because we already know how this flattening way was for me much more simple to grasp. And then so this is how you get the K, and so this is K00. So if I go here and let me, what is that? DW00 should be 5, 4 minus 3 minus 5. 5, 4 minus 3 minus 5. So that's it, how it goes. We can actually do the same for like this axis. It's much easier because it's just, you know, the reverse convolution. So, but instead, you know, as here you get these elements from all these different things. Here it's coming from these parts. So it's the reverse correlation operation. You can see the padding that's going on here like this. So let's just take a look at dx 1, 0. So that's going to be 1, 1 minus 1, 0, and 1, 1 minus 1, 1. So you can see that's basically the correlation operation, just works fine. So this is how I implemented the backpropagation with strided convolution. So it takes care of that part. And if you can think about it like, okay, if we implemented it like that, why don't we just implement the convolution in the forward way, where we can have both padding and we can have both strides and we can have both dilution. But the thing is that in a forward propagation way, I don't really know if you want to dilute anything. Does it make any sense? Maybe if you're making an autoencoder or like a generative model, maybe you will need that, but yeah, you can do that. You can dilute and you can see what happens. And this was my take on the convolution with the strided convolution and backpropagation, and I hope I could make some sense out of it. And so don't be afraid to go through the internet. I went through like 10 different homepages until I could find like a really nice kind of way to implement this. Stack Overflow is the first place by just type in Google that convolution and you will find something. So thank you for bearing with me today, and I'll probably see you sometime in the future. Bye bye.